Now the key to Gray's idea is to have new lock modes and a little extended protocol to deal with these lock modes to handle multiple granularities. The idea is to allow transactions to lock at any level in the tree, but with a special protocol using new intent locks. And the idea is that before getting a shared lock or an exclusive lock on some node in the tree, the transaction must have proper intent locks on all its ancestors in the hierarchy. So for example, we might get an intent to share lock on the database, an intent to share lock on a particular table, and then a share lock on a page within that table. Implicitly, all the tuples or records in that page are also share locked. Okay, so we lock from the top down using intent locks till we get to the node where we want to put an explicit S or X lock. And these new lock modes, there's actually going to be three of them. One is IS, which is the intent to get a share lock at finer granularity. Another is IX, the intent to get an X lock at finer granularity. And then we're going to have a special combined lock mode called SAX, which is like asking for an S lock and an IX lock at the same time. Now you might ask why that's useful or why it deserves its own lock mode. And if you think about it, the typical update command in SQL is a good motivation for this. Suppose you have a query like update employees, set salary equals 1 million, where employee name equals Bob. You might have to look at all the tuples till you find an employee named Bob, and at that point you do an update. So you're reading, doing shared locks till you see Bob, and then you want to upgrade Bob to an exclusive lock, and then you'll just get shared locks on the rest of the tuples. Essentially for the table, we want a share on the whole table and an IX that says we're going to eventually get an X lock on some tuple. So that's S and IX together. Gray's multi-granularity locking protocol works like this. Every transaction starts from the root of the hierarchy. To get an S or an IS lock on a node, it must already hold an IS or an X on the parent node of that node. To get an X or an IX or an SIX lock on a node, it must hold an IX or an SIX on the parent node. And so it's locking top down following this protocol. And then the transaction runs, and eventually it releases its locks in bottom-up order to make sure that it's unlocking in the reverse order that it locked. So it locks top down in the hierarchy, and it unlocks bottom up in the hierarchy. We're going to have two-phase locking going on during all of this, and we're going to have our lock compatibility matrix rules enforced as well. And I'll show you the lock compatibility matrix for these intent locks in just a moment. This protocol is going to be correct in the following sense. It is equivalent to directly setting locks at the leaf levels of the hierarchy. Okay, so it's going to allow us to get the effect that we would have gotten setting all sorts of little locks at the bottom of the hierarchy, but instead we're going to only have to set these higher granularity locks when we look at large numbers of objects together. To reason about the compatibility of these locks, it's helpful to have a simple example like the one here. We have a page P that contains two tuples, T1 and T2. And the idea is that if two locks are compatible on those two tuples, then their intent locks should be compatible on page P. So for example, an S lock on T1 is compatible with an X lock on T2 from two different transactions, and therefore an IS lock on P should be compatible with an IX lock on P from another transaction. Those intent locks are covering two locks at the lower level that are compatible, and therefore the intent locks at the higher level should be compatible. Using that reasoning, and really using this example, you can puzzle out what every compatibility entry in this table should be. And when you're done, you'll get a table that looks like this. So I encourage you to take this picture on the right and go through every cell in this table and justify why the value in the cell is what it is.